Okay. So here, let's kind of, if you don't mind, we'll review and then we'll start into the next part. So we started with, okay, it's weird because this book is a addendum to the statics book, so it starts with chapter 12. It's not a big deal. So we started with that, nothing new. Move through there. Okay, then I'm gonna jump through the problems. There is probably maybe a table of contents. Maybe not. Okay, well, there's not. That's okay. Then the next section starts talking about the erratic motion. And then it's not very much after that that we get into the projectiles. Okay, get past this. And believe it or not, I've checked. The numbers may not match. Like right here may not match the 12. But you'll find these exact problems in that online system. And so I've been picking them straight off the online system because I haven't figured out, say I like that problem. I have to search around to figure out which one it is in the online system. I wish it wasn't that way, but then he starts going to general curvilinear, setting up for the X and Y, which I don't think he starts. Okay, well, I take that back. So here's it's called Cartesian, rectangular components, whatever. It's just setting up for 3 components. Then he goes through and he's prepping you to start in the projectile, although he's giving you, no, that's not necessarily projectile. He's setting you up for the projectile because, of course, it has an X component and it has a Y component. This is the picture I was talking about one time where the red ball is just dropped. The yellow ball is pushed to the right. And what you notice about this is if this is a strobe, notice that the distances between these 2 flashes are the same, kind of indicating that the ball went to the right at the same speed. But notice what happens here. The distance get larger, indicating that it's speeding up. So with a constant flash or a strobe like that, you can see this effect. I don't think they had strobes back in Newton's time, but he may have observed something like that. That may have been where he started with it. I don't really know. You have to look back through the history of stuff. So we went to that. Then, okay, so we'll go back and work more of these problems as necessary. Then he may go into a spiral motion. Okay. Oh, okay, now he's going, okay, so this is the part I skipped over, and I don't generally spend that much time on this, but I should fill this in. That is general motion and the normal and tangential component. So if an object's going along this blue path, if you freeze it at that particular spot, when you look at the curvature of this thing and the tangent, the velocity is obviously going in the direction of a tangent to that curve. That's always the case. So if you're looking at the velocity right there, it would be a tangent line to that curve. Velocity back here would be a tangent. That's just the definition of velocity. So this will be the direction that the velocity goes. It turns out that at any particular flash of an instant, it appears as though this ball is rotating about some origin that really is kind of nebulous in a sense. But the first thing you can notice is as you move along the path, this apparent rotation about this origin changes. And you can kind of see that. But if you're looking at a particular instance, what you'll find is the velocity along the path is nothing more than the velocity of the marble or whatever that is. And if you notice, I guess he gets down here, the rate of the acceleration along that tangent is the change of velocity. I'll give you a particular instance. Let's say you get in a parking lot and you decide to do donuts. And so you're going around in a circle and a circle. Okay, your velocity is always tangent to wherever you are on that circle. But if you start at velocity equals 0, and then you speed up till you're going velocity of 60, then to get from there to there, you have to have an acceleration pushing you along this path. That acceleration is nothing more than the rate of change of that velocity. And so that's what you're getting right here. The acceleration along the tangent to that path, or in this direction, is nothing more than how, if you're sitting there looking at the speedometer as you're driving down this path, are you speeding up or are you slowing down? Okay. There's another component, acceleration, which has to do with this. We talked a little bit about the change in the vector. Now, what he does is he takes two of these vectors, changes them, and notices as you shrink them down to the point where they become very, very small, they're basically going back towards this location here. And what you end up with is this term right here. And you've seen it before. You probably saw it in physics as v squared over r. I mean, so think of it like this. If there's a piece of marble going through space and you want to change its direction, you got to turn on some sort of, say it's a rocket. So you got to shoot a rocket or produce a force that direction to get it to change the direction. The speed itself may be constant, but you want it to turn and head to a different place. So during this portion, you turn on a thruster. That thrusts perpendicular to the direction it's going, and it turns it. And so, yes, in fact, some of the forces along this, what he's calling the normal direction, equal mass times acceleration along the normal. The acceleration along the normal is that, but you had to produce a force in the normal direction. I'm kind of clustering this thing up. So let's say during this period, it's right here. You're producing a force along that direction to get it to change direction. That's all it is. You can think of this as being the term that changes the direction of an object. If you're driving in a parking lot going in circles, your tires are doing that, and you're actually turning the wheel, so your car's going around and around. The tires are actually forcing it to not go straight. So the tires are participating in that. So you have seen this in Physics 1, right? So what I want to do is expand on this thing. Okay, this is a special case of it, but the type of problems he has in this section. Let me just show you these types. The type of problem is focused on finding that. That's his biggest thing. Now in Physics 1, I guess, they gave you that. They basically, said you're going around a circle, track, R is equal to this, or in this case, he has rho. I don't know why he decided to change it. I think because maybe he's using R in the next section. So how do you deal with that in a surface that's odd? And what you do is you get down to, hang on, kind of jump around. And he doesn't really set it. Maybe he does set it in a box. Let me see if I can find it in the box. You know what? I don't think he has it in the box. He does not. Let me see if I can find it. He should put this in a little box. Hey, let me check something real quick. I'll make sure. Yeah, I've got audio. Okay, let me go back up. Okay. Where does he put it? He has to introduce it. I mean, you can't just start using something without. Okay, there it is right there. But is it not in an, okay, it is in a box. It's in a big giant green box. And it's in that procedures for analysis. I think it probably would have been better suited to put it in its own little box. So if you have some sort of function in which it's y and it's x out here, and say you have some equation that's that. I mean, I don't know what else to say except it's y is equal to that. Well, if you take one derivative and square it, and take two derivatives and take the absolute value of it, put it in this equation, this will give you the row that goes on bottom. And you can go back in math and show that, it has to do with radius of curvature about a path. And this has to do with, okay, you got to realize the second derivative is part of that. But you're not looking for concave up and concave down exactly. You're actually looking for where it's located here. You can go back and find the math that does this. He doesn't really introduce that here, but that's probably, I don't know which course that's in. I have no idea. It's got to be in one of the calculus courses. So he picks this up, and you'll notice what he's doing. He says, okay, during this little portion, apparently from here to here, here's your equation. So what do? The first thing he says in here, okay, the skier reaches a point A, the parabolic path, he has a speed of 6, which is increasing, so he's telling you that. Determine the velocity and the direction and magnitude of the acceleration. So his velocity is right there. What he goes through is he takes this, takes a derivative, squares it, takes two derivatives and gets it. And then he puts in x is equal to 10. Why? Because this is the point of interest. He gets that rho, or r. Then he comes down here and he says, hey, wait a minute. Now I've got my equation. Here's my acceleration. This is the term from physics 1, except we replace r with rho. We put in our 28. He told us this. This is the speed you're increasing. So he said we were increasing at 2 meters per second squared. So you could be decreasing as well. That'd just give you a minus. So you put in your 2, then you take your v, which he told you exactly what that was. Told you it's 6 meters per second. And then you put in your 6, you square it, you take this that you got from there, and you get the answer. And that's it. So there's nothing more complicated than this throughout this section. There are a few things along the way where you might monkey with your brain a little bit, but that's kind of the standard reasoning. Another thing, I probably should bring this up, okay. So here he found this angle, and it's 57. Now what he's doing is he's going through this. There are times in here, and I can't remember if it was in this course or statics or both, in which he may say, I want you to give me the angle with respect, like this. So here's what he's looking for. And say it's becomes 100 and 160. But it also could be looked at as minus or 360. Or here, hang on a minute. 160 minus 360. Believe it or not, and this was weird, sometimes you get this answer. He wants that answer. That's why, I don't take off points or try not to take off points for a reattempt. If you look at it and you're like, wait a minute. So if you get this and you're absolutely sure, turn around and do this to get the angle that he's looking for. If it turns out that you've wasted an attempt like that, you just let me know. I can delete that attempt. So essentially, that's all there is to this section. So the next section, to me, is very important because it ties that section that we just talked about with a section that's really important out of chapter 16. And what he's doing, he's starting with curvilinear coordinates. Now, along the way, we found this, dur dt is nothing more than u theta. We found that. And then we found du theta dt is equal to minus ur. Now, what he does initially is that's what he's going to do. He goes in here, and the first thing he does is looks for that. But his argument is, let's do a little bitty graphic here, and we'll show that, and maybe I may have goofed up there because there should be a theta dot in front of that. And in fact, I think, the more I think about it, there should have been a theta left out of that. So in fact, everything I said that I talked about before should have a theta dot in front of it. So I goofed there. Well, you use, okay, so you can use 12.14. Okay, wait a minute. Oh, the one back here? Well, the reason, okay, hang on, let me get back to it. That was it, wasn't it? The reason you kind of want to do that, let me give you a case in point. I tell you what, maybe this is the best way to do it. Let me just come up with a new page or just start. I have no idea what's going on there. That looks like something else. Here, I'll just add a section here. This is good. So let me say it like this. Let's say you had an x and a y. So the question is more why you use base vectors. Is that the question? In a generic sort of sense? Oh, okay. So just that specific. It wasn't, it was just that. Oh, okay. Well, that makes sense. So in every single case, in this particular case, he's given you all this information. So your problem is, let's say you wanted to use the x and the y. Now let's say somebody said, well, you got all this, so I want you to find the acceleration as this way I plus this way j. So that's what we're most used to. So you look at this and you're like, okay, well, wait a minute. I've got to figure out some information here to get this. So in order to get that, I have to know x dot, and I have to know y dot, double dot. But I really don't have x as a function of time here, and I don't have y as a function of time. I don't even have the velocity as a function of time. Vx, let me take this off, or Vy as a function of time. So I'm stuck. So the reason I'm stuck is because the problem was done this way. So there's really no way for me to directly find this information. Do you buy into that? Yeah. So now that we've got that, we've got to do something else. And in fact, we really don't have any other choice but to come up with the coordinates that best suit the problem. Side issue. Let me give you a side issue. Let's say you're turning things in the parking lot. Yeah, we're just making a new coordinate system is what we're doing. And so, so what we're doing is we're basically realizing that we were given this information and we have this as our tool. We can actually do this. Now, when I get this, okay, and this might be beneficial for you to look at as well. Let's say you get this. And if you don't mind, I'll copy this over onto this page. I'll say A is equal to what? 2UT. Let's see, can you do that? Yeah. 2UT plus 1.273 UN. And I really don't care about the meters per second or something. Now, maybe this is instructive. I hope this is not confusing. I hope this is instructive. But if you don't mind, bear with me for a minute. So then the person who asked you this question, maybe it's your boss, maybe it's something, he said, I really don't need that. I need this. And so I need you to give me this. This is what I need. So the problem is I've got a situation where I have the answer now. I've worked the problem out because the geometry of the problem was more conducive to find that. But now I got to get rid of this. And so, in fact, if you notice, okay, so if this is a special case, but he says by definition the velocity is always directed tangent to the path. So in other words, he's saying find that, and this is the velocity, it's tangent to the path. Turns out he says hence at A, velocity makes an angle of that. So it's 45 degrees. So now let's do this. Let's go back over here and say, it doesn't really matter. I can just draw a line that's 45 degrees. That's roughly 45 degrees. And here is U tangent. And why did I put that as R? So this is the tangent direction. Okay, it is true the velocity is at this point. However, I can just move that anywhere I want. So I can move it to there. I can move it here. It doesn't matter. It doesn't change the value of that vector wherever I move it. So I'm going to place this vector here and the other vector, which goes up through the skier's body, is like this. Now, here, this is a big key. This is the key that was based upon what we did the other day, even though I made a mistake and I left the theta dot off, which I'll correct that. You have a vector, which is unit length, that's 45 degrees down, which basically looks like this. So this is UT, and its value is, and believe it or not, it's 1 over square root of 2 down and 1 over square root of 2, and that's because this is 45 degrees. And so if I wanted to, I could say U tangent is equal to the x component goes back to the left, 1 over square root of 2 I, and then the component here goes down, 1 over square root of 2 j. Now, that's kind of critical to see that you're transforming between one basis vector here, and then the I and the j, which is the I would be out this direction, and the j would be out that direction. So does that make sense to you? That you're just, that these base vectors can, in other words, you can move, you can solve the problem in polar coordinates, oblique spherical coordinates. You can solve the problem in whatever coordinate system is best for the problem. But if you feel most comfortable getting your answers in the IJ coordinate, you just look at the base vectors, where they point, and try to transform them back to the x, y. And if there's a k, you can do it k. If it's three-dimensional, it's just the same thing. So if you recognize that, you've got a major accomplishment. That's something that doesn't happen to most people that come through the course. Yeah. Uh-huh. Uh-huh. Oh, that's simple. Okay. Hang on. Okay, so we know that. Okay. Because, okay, So if you're going along a path, then along the path, in the tangent to the direction, that's what the T is the tangent. I'm trying to erase stuff. So you got the tangent going that direction, or, U tangent. Okay, if you're speeding up or slowing down, you're changing the velocity along the path. And so that means the 2 goes on top of this. So this is the amount that you're speeding up. Think of it as like this. This is what your speed is. You're changing your speed. You're speeding up or slowing down. You're changing the acceleration only along the tangent direction. This is your tires making you turn. Or if you're a rocket ship, a little thruster off to the side. You're traveling this way, and a rocket ship shoots thrusters off and you turn direction. But you didn't change your speed. So you can actually have an acceleration without changing your speed. Yeah, you can look at it like that. If you think linear is along the path, is along your path. So, in essence, in physics, you kind of focused, I don't know if you actually did it this way, but you focused in physics on this term. But you didn't put it, maybe, I don't know. Acceleration. Okay. So now we're saying that there is a direction to it, but there's also a direction to the fact that you could be in your car going in circles, but you could be speeding up going in circles. You obviously have to. You start at 0, you push on the gas, you speed up. So as you're speeding up, you're accelerating along that path, but consequently, believe it or not, it makes sense. As you speed up, also this term increases, and so your centrifugal acceleration increases till your tires can't hold it anymore, and then you spin out. And actually, believe it or not, in the old Car and Driver, I don't know if they still do it, or maybe it was Motor Trend. Anyway, they would do a test on a car. They would put it in a parking lot, and they would go in circles until it broke free. And they would say that's how many side G-forces the car can handle. And you put a Ferrari in there, it could hold lots of G-forces. Station wagon would spin out. Truck would spin out. Truck is the worst about being able to hold a side or speed go in a circle. Did that make sense? So I probably was distracting you with this, but anyway, you can convert that also just to complete the conversation. UN would be negative 1 over square root of 2I, because it'd be a component going back that way, plus 1 over square root of 2J. And then you could stick this in here and stick that one in there and work out the math, and you could get these values that would be right there and right there. So I guess the point I was maybe explaining something that wasn't the question, but to complete answering the question that you have no question about is that often your problem is presented to you in a way that a coordinate system is perfect for it. And you get an answer. But you may want that answer in another coordinate system. So after you get your answer, you can transform back to another coordinate system. So, physically what you can do here, I'm going to try to see, or maybe he did it. Did he do it? Oh, he did. Yeah. So here's what he's got. He's got the 2 meters per second squared, and he's got the 1.2. That looks like that's pretty close to scale. He puts the angle in there, and then he draws the little square box, and he gets this angle right here somewhere, right there. So he gets that thing. So he may ask you for the question. This is one of those things. What's the question? What's the angle from the horizon? So he's got 45 and then his 90, and then his 57. But then he throws in that minus 180. And so it's like, you know, so what he's doing is he's finding that angle. In the book, a lot of times he'll do that. He'll draw the thing and then show the angle. So this you would know. If he makes the effort of drawing where that is, there he would know. So this would be the 45 plus 90 plus 57.5. Or maybe he would draw it like this. Here it is. Here's this. Find this angle. But that's the angle he's presenting to you in this problem. So, yeah. So is this particular one, are you looking at the book online? Okay, so does it look exactly the same as this? Or kind of? Okay. Oh, okay. Yeah. Yeah, that's what I'm wondering if I don't know how this works. I mean, whether they made that first and made this from that, or did they make this first and make that? Because that's a lot of work. I mean, or maybe this is in some format that you push a button and it turns into a paper, push another button, it turns into that. I don't know. So most of these are the same. Well, here's a typical case. Okay, so this is a case in which it's a little bit different. The car increases at a speed at a constant rate of 7 feet per second, starting from rest. Determine the time it needs for to reach an acceleration of 8 feet per second. So you're starting from rest and taking off. Did you say a constant acceleration? So wait. Car at a constant rate of. So you have an acceleration. His constant rate, the car increases at 7 ut plus, ooh, that's weird, v squared over 300 times un. I keep wanting to call that r, but you'll see why I keep wanting to do that. So then your biggest key is, when does this thing have a constant rate? Well, 7 squared plus v squared over 300 squared got to equal to 8, because that's what he wants. Why did I write 80? Or maybe you could square that, and then maybe you could move that over, and then maybe you could square root it. Oh, shoot. A minute. What do you mean by add them? There's a component of I on both kind of like the last one, where we were getting UT and UN. Both UT and UN have a component of I. Both, okay. So both UT and UN have a component of I and Z. Oh, they do have it. Well, the reason being is you don't want to move into the I and J till after you're done. If you even have to. Sometimes you might not need to. So there are times, okay, so let me say it like this. It is a rarity for him to ask you to move out of a T and an N coordinate, UN and UT coordinate, into an I and J. As a matter of fact, in all those times and all those problems, I think I only saw one problem that he ever did that. So I may be mentally misdirecting you, but what you probably want to do is stay in the coordinate system that best suits the problem till you're completely done. Does that make sense? And so what Well, actually, so I misdirected you in that. There's really no reason to go to the I and J. Does that make sense? Well, because, okay, so here's why. Because we know, if we know this car's going in circles, we chose UN because we know this. And so, yeah, because it's V squared over R. Okay, V squared over rho. So we know that. And we're going to that because he just tells us the car's increasing its speed a constant 7 feet per second squared. So we know this UT is associated with increasing the speed of the car. This one is associated with the centrifugal accelerator. And so since we know these two things go together and we know this thing is going in this circular path, it's very natural to use this and this for the base vectors because we know what gets multiplied against them. Does that make sense?
So is it actually a base vector or is it just another?
It is an actual base vector. It's of unit 1. The difference is as the car goes around the thing, the tangent, okay, wait a minute, U tangent and U normal change because, oops, that's a terrible drawing. So here, U tangent, U normal, they just change and point at the same thing. That's okay because as they move around, in this particular case, they're moving around constantly. Now, somewhat at any particular spot, let's say we look straight down at this. So here's a track. So there's a track, we're looking straight down. And he says, I want you to find the I and J component. What's your first question you'd have to ask the guy?
Where?
Exactly. Because then, if he tells you it's right here, guess what? Oh, geez, that's supposed to be a straight arrow. Okay, that's a U tangent. Okay, let me try again. My hands here. There you go. Okay, there's your U tangent, which is exactly with the J component, and there's your U normal, which is exactly opposite. But if somebody said, well, I want it right here, well, guess what? Yeah, this U tangent, this is U normal. So you got it right on the head. You have to know where somebody's asking you. If you're going to switch coordinate systems and you want to switch it back, the problem is the U tangent is a function of time and the U normal is a function of time. I is not a function of time and neither is J. So the only way you can transform from here to there is I've got to have the physical location of the car in order to transform. Does that make sense? So this is a weird thing because, you could, yeah. Like I've done this before on a test. Now I'm not doing it because I'm not giving you those things. I've done this where I've made you go through and get it. So you get the answer, say like that last one or something. Say your acceleration is equal to, just making stuff up, ut plus 4 un. And then I'll say, what's the acceleration in I and j, plus j at theta is equal to 0, which would be this point right here. If you understood it conceptually, you look at it and you say, hey, wait a minute, that's the 4. Oops. I'm sorry, that's the 2, goes with this, and that would go right there. This would go back to the left, and it'd be a minus 4, and you're done.
Oh, okay. So we're not using the I within the vectors. itself is ice.
Yeah. Yeah. So it's kind of a weird thing. The chance of you ever being asked this question is pretty slim, unless you have some stupid professor like me putting it on a test just to try to trap you. But at the same time, now you're asking questions. I know you kind of get it, so we can go on from there. So, in this particular case, what he's doing is he's going through and he's figuring out this fact, and he says, "Oh, I want it to be." So what's happening is the car starts at zero, speeds up, finally reaches a speed in which the velocity will be such that the square, these terms become 8. So in other words, if you look at that, the key here is to recognize that. And then you just solve for your time, and that's it. Then you can go back, take that time, and put it in here, and you can get that 34 feet per second. That's the speed that was required to get that. So most of these problems are kind of that, something going in a circle or something going like that, and you have to use that equation. But what's funny, okay, is your UT is always a tangent. So if he asks you to find the velocity at some point out here, you'll do a tangent, and then you'll make something 90 degree to it, and that'll be the normal. And that's pretty much it. So all these problems are fine. Now I kind of feel like I should fix my error in which so just to make sure I fix my error, do y'all mind if I do that derivation again? It won't take me but a second. I mean, that annoys me when I goof up like that, but I'm getting to the point where I expect it. So, if you go to polar coordinates, you have the x. I can tell you right where I've messed up my. So you're measuring to some location, some distance, and I'll call this r. And then you have a UR vector. Now the difference here, and this is maybe a good time to talk about it. The difference here, oh, never mind. It's 10 pill. Huge. Y'all got a class after this, don't you? Because I know I got one too. So sorry. You know what? I'll pick up this same thing and correct myself on Monday. But if you want to see it, if you want to go ahead and see, wait a minute, where is it? Where's the book go? Oh, right there. I'm going to start in this thing and work my way through it. So you can reread ahead if you wanted to. But the goof I made was right there and right there. And I want to fix those goofs and show you what I goofed on it and show you why I goofed it. I can't show you why I goof stuff. I just goof it, and then I realize it later, and I have to go back and fix it. So I'll go back and fix that, and we'll just go on from there. So sorry about that. But the problems on these are they fit well together. They're okay. They're not hard to do, but you have to do a little bit of calculus on them. Differentiation and stuff like that. There's a little tricky part to that, and you can even see, look at the amount of necessary evil that this guy had to do on this one. That's a lot of, but there are different codes out there now that can help you with that, assist you, make sure you get those right. It's just the way things are. So I'll fix my goof next time, and then we'll just go into these problems, and I think these problems might be on the next assignment, or they might be on the assignment after. I'll have to look and see. So And then I'll keep doing this thing where I talk about the base vectors so you can see why you're solving it this way. I'm starting to see how you're thinking, and maybe, which is good for me because sometimes I get stuck in a rut thinking the way I do, and I think everybody should think the way I do, but I need to maybe do a little better job explaining. Oh, well, yeah, and see, that's the other problem. I don't even know, like, I know you learned v squared over r, but I don't know if you did the coordinates, and I'm like,
Yeah,
what?
we need really trying to
Uh-huh.
just make an important
Oh, okay.
easier for us
Okay.
to do it. And usually wires are not.
Oh, okay. That's interesting. Huh.